name. Yep. Sometimes you'll see like a little mark above the O, like one of those little foreign-looking words or foreign-looking symbols. I don't know what that's called, but the way you say that is L'Hôpital. L'Hôpital. So this was a student of one of the Bernoullis, and so supposedly one of the Bernoullis kind of came up with what we're about to do here, but L'Hôpital kind of refined it, and so he's generally given credit for it, or at least it's named after him. That's the kind of things kind of work in the math world. And anyways, I mean, there's so many Bernoulli principles and Bernoulli equations. There was a Bernoulli everything. So let's call this L'Hôpital's rule, right? Instead of Bernoulli's rule. Anyway, so this is kind of an interesting fit as far as the timing goes. So if you think about, like, most of our unit has had to do with differential equations. This is not about that at all. I put this here because, as you know, this unit is pretty short. We only have the 3 sections, and we're done for the moment, at least with the differential equations. So this seemed like a nice natural fit. So this is a little bit of like a right-hand turn, and we'll go with it. So if you remember, way back, start of the year, we looked at limits, right? And we've continued to kind of process through limits, and sometimes we came up with some expressions like this, where there was a 0 in the denominator, and we always said, oh, that's a problem. And in the past, the main thing we did was we factored, right? You remember doing this? You factor and you cancel, and then you reevaluate the limit, and it all works out fairly nicely. What we're going to deal with here is the scenario where, what if it didn't factor real nicely? Could you still do something with it?
I'm assuming yes.
Yeah, just go in the corner and cry. No, not that. And so L'Hôpital's rule is, how do I put this? L'Hôpital's rule is, once you see it, like mechanically, you're going to be thinking to yourself, probably that's pretty easy. But be aware, the bar is really high for expectations of notation and symbology. Does that make sense? You're going to find the process, like once you see it, you're probably going to think to yourself, really? That's all I got to do? That's not that hard. But the bar is high for the symbology. So we'll be looking at that in the next couple of days. Let me just share with you like when we'll be using L'Hôpital's rule. If you evaluate a limit and the limit of the numerator is 0 and the limit of the denominator is 0, that's going to be a time we use L'Hôpital's rule. Or if the limit of the numerator is infinity and the limit of the denominator is also infinity, that'll be the other condition that we'll be using L'Hôpital's rule under. There are some other conditions, all of which can actually be manipulated to get back to those. 0 times infinity is actually what we call an indeterminate form. You want to say that the answer is 0, don't you? Because we've been taught from day one that anything times 0 is 0. It should be better said any real number times 0 is 0. Infinity, not a real number. 0 to the 0, infinity minus infinity, infinity to 0, and everyone's favorite is this one. What do you want to say the answer is? You want to say the answer is 1, don't you? But what does 1 to the infinity really mean? Doesn't it mean 1 times 1 times 1 forever? And the moment you stop and say, and the answer is 1, you didn't do what it told you to do. In fact, if we have time, I might actually show you an example where you get that. This would be beyond the scope of the class a little bit. I might show you an example where you get 1 to the infinity initially. You do a little bit of L'Hôpital's rule work, and you end up with something other than 1. Right? Pretty crazy. So anyways, that's just kind of a preview of what we'll do the next couple of days. Hope you guys have a good day. I'll get your test from you on the way out.
False.